Hi everybody, this is John Whitaker for the graduate probability class, and this is our 10th video lecture. And today we're going to start talking about relationships between random variables. And so there will be things about joint probability mass functions, joint probability density functions, joint cumulative distribution functions that we're going to start talking about. And so that's what today's video lecture is going to cover. Let's go ahead and get started. So here's the definition. It says, given two discrete random variables, say x and y, the joint probability density function, mass function of x and y is denoted by little f of x comma y and given by f of x comma y is equal to the probability that x equals to x, comma, that comma means and y equals to little y. So that's what it is. Next thing I want to do is just list some facts about the probability, the joint probability mass function. So let f of x comma y be the joint PMF, probability mass function, of x and y. Then, so here's some two things we keep in mind. One is that 0 is less than or equal to f of x comma y, which is less than or equal to 1. And that's true for all x and y that are real numbers. And then 2, the sum over all the output values for x, the double sum over all the output values for x and all the output values for big y, of f of x comma y, that's going to be equal to 1. All right, let's look at an example where a joint probability mass function is involved. So consider an urn containing, so 1 red ball and 2 white balls. Okay, a ball is selected at random and a card is selected at random from a standard deck. Okay, define x of a red card to be equal to 1, x of a white card to be equal to 2, y of a heart to be equal to 2, y of a diamond to be equal to 3, and y of a black card to be equal to 4. And someone might say, find the joint PMF of x and y. So here's what I'm thinking. What I'm thinking is that I'm only going to define the joint PMF for values of x and y that are output values for big X and big Y. And the rest of the time, the joint PMF is 0. So we're not going to be interested in that part. So here, let's see. So X can be 1, Y can be 2, 3, or 4. So there's 3 output values. X can be 2, and Y could be 2, 3, 4. So there's another 3. So it's going to be 6 things that I write down. So first one I'm going to say is note f of 1, 1. What does that mean? That's the probability that x is equal to 1 and y is equal to 1. Well, what is that? That means the probability we've got a red card, red ball, and then we got a, it's not 1, 1, I'm sorry, it's 1, 2. Because y is the smallest thing it can be is 2. And so that means that we got a red card and a heart. Red card. We got a red ball and a heart. Okay, so we think of this as kind of a sequence of events. Everything's equal like that. How many ways could I get a red card? Red ball. There's only 1. How many ways could I get a heart? There's 13. How many ways are there to get a ball? There were 3. How many ways are there to get a card? 52. And so this ends up being 1/3 times 1/4, which ends up being 1/12. So f of 1, 2 is 1/12. Okay, let's continue. Okay. So continuing, what's f of 1, 3? Well, that's the probability of a red and a diamond. Again, that's equal to 1 times 13 again over 3 times 52. That ends up being 1/12. Same answer. Half of 1 comma 4 is the probability x is equal to 1, y is equal to 4. That's the same thing as the probability of getting a red ball and a black card. That's one way to get the red ball, and there are 26 ways to get the black card. All over 3 times 52. This ends up being 1/6. F of 2. So we run through all the possible output values where the x value is 1. So now we go to x being equal to 2. Because we've got a white ball. And then 2, that's the same thing as probability of x equaling 2. Y equaling 2, that's the same thing as probability of white. Heart, let's see, that's equal to 2 times 13 over 3 times 52. That ends up being 2/3 times 1/4. So I think we end up getting 1/6 for this as well. F of 2, 3, the probability of x is equal to 2, y is equal to 3. That's the probability in this case of the white. And then the diamond, that again is 2 times 13 over 3 times 52, using the classical definition of probability. This is 1/6. And finally, we have f of 2, 4. That's the probability x is equal to 2, y is equal to 4. And that's equal to the probability of a white and then a black card. White ball, black card. That's 2 times 26 over 3 times 52. And I believe 26, 52 makes 26 over 52, 1/2. I think it's just 1/3. Now don't forget, we had one on the other board here, and that was f of 1, 2. I'll just write this down. So f of 1, 2 was equal to, we had it as 1/12. Now, one of the things I want you to notice is that if we add up these values, so I'm going to do that in just a second. Remember we said that the sum, the double sum over all x values and over all y values of a joint PMF is equal to 1. Let's check that out. Okay, so note that the sum over all x values here are 1 and 2. The sum over all y values, that's 2 through 4, of f of x comma y. So here's the way that we do this double sum. We think of it as kind of an iterated sum. We let x be 1, let y run through all of its outputs. Then let x be 2, y run through all its outputs. So what I'll do is I'll say, hey, this is f of 1, 2. Plus f of 1, 3, plus f of 1, 4. I'm done with x being 1. Plus f of 2, 2. Plus f of 2, 3, plus f of 2, 4. Okay, that's what we have. Now I need to stick in the numerical values for this. They're on the other board. This is 112 plus, the next one is 112. Plus, the next one is 1/6, so I'll make that, well, I'll just write down 1/6. The next one was 1/6 plus, so that's 4, that was 2, 2 I just did. 2, 3 was 1/6 and 1/3. Okay, so let me think of this in terms of 12. There's 2 12s, this is 2 12s, so that makes 4 12s, 6 12s, 8 12s, and that's 4 12s, so we do get 12 out of 12, which equals to 1. And that's what we're supposed to get when we sum up all the values for the joint PMF of x and y. Okay. All right. Well, here's a definition. If we let f of x comma y be the joint PMF of random variables x and y, okay, then the PMF of, and so I'll write down 2 definitions. 1, x is f sub x of x, which is equal to the sum over all y values of the joint PMF. And part 2, okay, so right down here, of y is denoted by f sub y of y, and what's it equal to? It's the sum over all x's of the joint PMF. So you can recover the PMF for individual random variables from the joint by simply summing over the other value of the variable, the values of the other variable. Let's look at an example of that. Well, maybe before we do an example, let me stop. Instead of calling this a definition, I shouldn't have called it a definition. This is not a definition. I made a mistake. This is really a fact, and it's something we can prove. So let's make this change. So if you give me the joint, I can get out the individual PMFs for the random variables. Let me show you the proof. So here's the proof for part one. So we're going to let, well, in general, we're going to let f of x comma y be the joint PMF of x and y. Now, so here's for one. Note the PMF of x, and I'm going to write it down as f sub x of little x, and I'm going to write it down with a subscript of big X so that I can distinguish it from the PMF of y. Well, what's it equal to? It's equal to the probability that x equals to little x. Well, this is the same thing as the probability that x equals to little x, and y is a real number. So no matter what y is, these things are happening. So it's and. So probability x is equal to this, and y is equal to a real number. Well, what's the chance that y is equal to a real number? It's 100%, but we're not being asked the probability that just y is equal to a real number. Let's express this event that y is equal to a real number in terms of a union of events. So it's the union over all I of the y, or y equal to y sub I. And what I'm thinking is the following. Y sub i's are the collections of y sub i's are the output values for big Y. And so if we union over all of those, y equal to y sub I, we're getting the outcome that y is a real number. Okay? So this is an and. The way that we can rewrite that is this is the same thing as the probability of the union of over all i's of x equal to x and y equal to y sub I. So that's what this is. That's the way that it can be rewritten. So what we're saying here is the intersection between these this event union with this one is the same thing as the union of each individual event. We'll take the probability back. Now look, y sub i's are different from each other. And so the chance, let's say x is equal to little x, like 1, and y is equal to little y sub i's, maybe let's say that's 2, and x is equal to 1, and y is, x equal to 1, and y equal to some little y sub I is different, let's say 5. Those can't happen simultaneously. So these are mutually exclusive events. And so that equals to the sum over all i's of the probability that x is equal to x and y is equal to y sub I. So another way of thinking about that is to say that's the sum all over the y sub i's. So just change your index to y sub i's here. But the probability that x is equal to x and y is equal to y sub I. But when you look at this, okay, what is this probability? This probability is nothing more. So these are the output values for y sub I. The probability that x is equal to x and y is equal to y sub I, that's nothing more than the joint PMF of x, y, sub I. And so in our terms of our notation, I've run out of room here, but in terms of our notation, we'd say Sorry, I'll complete it right here. That sum, we're saying, is equal to the sum over all y values of f of x is an individual fixed x, and then the y is what's changing. And so that's what f of sub x of y is. Okay? I'm sorry, f sub x of x is. Okay, for part 2, with f sub y of y, the PMF of y, the proof is analogous. What I just did, analogous to the proof of 1. So I'm not going to do that. It's something that's easy to see. Okay? Let us look at an example. So let's let f of x comma y, which we're going to find to be equal to x plus y over 21, where x values are equal to 1 and 2, and y values are equal to 1, 2, and 3, be the joint probability mass function of x and y. And the directions are, is find the PMF of y. Okay, so I know how to do that from the previous fact. It's just going to be the sum over all the x values. So let's check it out. Note, f sub y of y is equal to the sum over the x values, this is by definition, of the joint. So in our particular case, that's going to be equal to, is the sum of the x values are just 1 and 2. And so it'd be f of x comma y, but I know what that is, it's x plus y over 21, but there's only 2 things to add here. Let's see, this is going to be 1 plus y over 21 plus 2 plus y over 21. So this ends up being 3 plus 2y over 21. That's the answer. And that's where, I'll say where, y is equal to 1, 2, and 3. That's how we do that. Well, we've had now the joint probability mass function when we're talking about 2 discrete random variables. We want to turn to next, our x and y being jointly continuous. So let's look at that. We say 2 random variables x and y are jointly continuous if there exists a function little f of x comma y defined on R2, so I won't say anything about where it's defined, such that for all subsets of R, I'll say for each. A is a subset of R, and B being a subset of R. Then the probability that the random variable X is an element of A, and the probability that Y is an element of B, is equal to, well, instead of a sum here, we're going to use integrals. So it's the integral over B, integral over A of f of x comma y dx dy. So we're going to do the double integration here. In this case, f of x comma y is called the joint probability density function of x and y. That's what we have. I'd like to list some facts about the joint PDF. So we'll let f of x comma y be the joint PDF, probability density function, of x and y. Then, here's two things. We're not going to prove this. Is two things. One is that the values, the output values, have to be greater than or equal to 0. And then two is that if you do the double integral from minus infinity to infinity, of f of x comma y dx dy, what you end up getting is 1. Okay. So we're going to be involving this double integral. We think of it as an iterated integral. So the right thing in a second. And a lot of times, all the time, we'll be able to switch the order of integration, and that might help us. So being able to do these double integrals is something that's going to be a factor for us. And what this is some curve above the xy plane. Okay, some curve above the xy plane. And really, what we're saying here is whatever that curve is, when you, and it's always positive, that curve is, when you integrate it over the whole xy plane, what you're getting is a volume. And what we're saying is the volume of that object that's formed by looking at the curve or the surface that's above the xy plane over the whole xy plane, I should say. If you look at that surface, the distance between that surface and the xy plane, not the distance, but the object that's formed between that surface and the xy plane, that volume of that object is equal to 1. That's what this says. Well, let's look at an example. Here, we're going to let f of x comma y, and it's going to be equal to 5/16 xy squared if 0 is less than x is less than y is less than 2, and 0 otherwise. Okay, we're going to let this be the joint PDF of x and y. Okay? And so in particular, what we're going to do is we're going to show this second fact that if I do the double integral of this function, we get 1. Okay. Okay. So note, if we look at this double integral, from minus infinity to infinity, from minus infinity to infinity, f of x comma y dx dy. Well, this function, a lot of the times, is 0. So if you think about the xy plane, when is it 0? So here's the way we handle this. Look, it said that this guy is non-zero when 0 is less than little x is less than y is less than 0. Let me try to graph that. How do we graph this? Well, we're saying we want to look at the region where the x values are between 0 and 2, so let's call this 2, and the y values are between 0 and 2. And so the only place where that happens is along this square. But not only does that have to happen, it says x has to be less than y. So x has to be less than y. Let me draw y equal to x. So y equal to x would be this diagonal line. We know this line, y equal to x. Okay? And so the square is the only part where possibly the joint PDF is non-zero. But it's not just over that whole square. This line breaks the square into 2 regions, and we want to part of that square, the region of that square, where the y is bigger than x. So what we do is we just try points to see where that occurs. So here, if I try this point, this is like 1.7, and maybe that point right there, maybe 0.2. Okay, so 0.2. Does the point 1.7, so here's what I try, 1.7 comma 0.2. Does that point satisfy this point in this region? Does it satisfy that the x value is less than y? Well, it doesn't. So it's not this region. So let's try this region. So maybe I put down right here, this point right here, I'm going to take as being 0.2 and 1.7. Does it satisfy, so this point right here, does it satisfy in this top region that the x value is less than 1? Yes, it does. And so with every other point in this region. So here is the region of integration of which the joint PDF is non-zero. So if I look at trying to integrate where the PDF is 0, when I integrate it, I don't get anything but 0. So the only place I have to integrate is over this region. Okay, how do we do this? So I want to rewrite it in terms of the specific joint PDF that we have here and indicate the region where we're integrating over the non-zero part of the PDF. And so here's what we do. I'm going to say, I'm going to integrate with respect to x and y. And so what I'm thinking is the first integral right has to do with the last integration that we do. And I said we do y. And so the y values run from 0 to 2. Okay, here, remember this was 5/16. I think it was xy squared. Let me look. Yes. Okay. And so I'm writing dx dy. I think we'll get to integrate this, which is fine. So the y values run from 0 to 2. So think about a particular y value. That one. Look for that particular y value. What would the x values run from? Well, the x values would run from along that horizontal line. They would run from 0 to this curve. So that means the x values will run from 0. And what is this curve in terms of x? So x was 0. What's this curve in terms of x? It's x equal to y. So I put y at the top value of what x will be. And that's what we need to compute. All right, so I do the integration with respect to x first. So this integral from 0 to 2, I need an antiderivative of 5/16. So it's 5/16 xy squared with respect to x. So here I would have 5/16 x squared over 2 y squared, because the y squared and the 5/16 with respect to x are constant. So really I'm just integrating x, which is x squared over 2. I need to evaluate this from 0 to y. And then once I get an answer for that,
we integrate with respect to y. So I think I have enough room to get this here. When I stick in y, so we have an integral from 0 to 2. When I stick in y, remember these are x values. So I'm using the fundamental theorem of calculus here. So x equal to y. When I stick in x equal to y, we get 32, this is 2 and 16. And then the x squared, we're going to stick in 1 for that, so that's y squared times y squared is y to the 4. And then, when I stick in 0, so minus, when I stick in 0 for x, I'm just going to get 0, so minus 0 dy. Okay, so here we end up getting the integral from 0 to 2 of 5/32 y to the 4th dy. Well, the antiderivative for that will be 5 over 32, that's the constant, y to a higher power, 1 higher power, divided by 5, evaluate from 0 to 2. So that ends up being, the 5 will cancel, so we have 1 over 32 times y to the 5th. And we're going to stick in 0, 2. When we stick in 2, we're going 1 over 32 times 2 to the 5th, minus 1 over 32 times 0 to the 5th. Of course, this last part is just 0. 2 to the 5th is 32, so we end up getting 1 for this part, minus 0, so that's 1. And that's what we thought. The double integral, that's what has to happen. The double integral of the joint PDF has to be equal to 1 when you integrate over the whole real line. Okay. As a fact, just like what we had analytically before, if f of x comma y is the joint PDF of x and y, then the PDF, so the individual PDF of, in this case, x is f sub x of little x, and it ends up, instead of the case, that we had the discrete, we had the sum over all of y's. Here we're going to have the integral of all the y's. So it's integral what? Of the joint PDF over the y's, and 2, the individual PDF of y is f sub y of y, which equals to the integral from minus infinity to infinity over the whole real line of f of x comma y dx. That's what we have. Let's prove again part 1. So, as proved, we let f of x comma y be the joint PDF of x and y. So for part 1, note, so here for joint, remember what is f sub x? What does it represent? F sub x is the function that you integrate to get the probability that x is in A. You integrate it just over the set A. So here, if we just say, what's the probability x is an element of A? So in that question, in terms of the joint, would say, okay, what do we have? We're having the integral from minus infinity to infinity, the integral over A f of x comma y, well, maybe I should write this down a little slower. Let's take a step back as we had before. This is the same thing as the probability that x is now in array, and because all we're concerned with is that x is in A, y can be anywhere. So if y is known with the real numbers, that's equal to, all right, now I can apply the definition of the joint PDF to say, hey, that's the same thing as integral from minus infinity to infinity, integral over A of the joint PDF, dx dy. Earlier I said we could switch the order of integration in these cases, and we can. So I'm going to say this same thing, it's integral over A, integral from minus infinity to infinity, of f of x comma y, dy dx. And think of this as an iterated interval. So just, we do this inner part first, and then we do the outer interval. Okay? So when I look at this inner interval, what I find is what's in parentheses is the guy, the function, that I integrate over any A to find the probability that x is in that A. Well, that by definition is what it means to be the probability density function of x. Okay, so it's this interval. And so there's two parts to this. Of course, I'm going to make the same statement that I made before with the discrete case, and that is part 2 is analogous to part 1. And I'm not going to do it. For part 2, the proof is analogous to the proof of part 1. Okay, so I'm not going to do that this day. All right, let's look at an example. So the same example we had, we'll let f of x comma y be equal to, I think we had 5/16 x y squared if 0 is less than x is less than y is less than 2, and 0 otherwise. And let's say someone asks for us to find the PDF, oh, I should say what this is. Let this function be the joint PDF of x and y. Find the PDF of y. Okay? We'll correspond F, little f, so big Y, little y. So what would we say? Well, note by our fact, big F, little f of big Y, so y of little y, that's equal to the integral. So here it would be from minus infinity to infinity of f of x comma y. Then it would just be dx. So again, I'm going to write down the picture here. I'll rewrite this statement. We'll write the picture here and do all the work on the other side. Picture. What do I mean by picture? I mean the x and y plane. We're going to look at the part where f of x comma y is non-zero. Okay, so look, I'm just rewriting this, okay? You've already written this down. F of y is equal to this angle. So I'm integrating with respect to the opposite variable. That's what I remember. And so here's my picture. My picture, again, we already had this, where it's non-zero. This is 2, this is 2. It's this one. The top part of the triangle, this square. Okay, so everywhere else, the joint PDF is 0. So we just need to integrate it over this. Okay, so we fix a particular y. Okay. For that particular y, what do the x values run from? Well, again, we know the non-zero part, this area of integration. The x values run from 0 to y, and here's what's the function when being non-zero. It's 5/16 xy squared, and we're integrating with respect to x. That's equal to 5/16 x squared over 2 y squared, evaluating from 0 to y. Here we get 5 over 32. I stick in 4x, the value of y. So y squared times y squared, that's y to the 4th. Then I subtract from it, 532. When I stick at 0, I just get 0. And so what we end up getting is f sub y is equal to 5 over 32, y to the 4th, where y can run from 0 up to 2. And that gives us the individual PDF of y. And of course, we could do a similar thing to find the individual PDF with x. But I'm not. Okay, the next thing I'm going to do is define the joint cumulative distribution function. So here's the definition. The joint cumulative distribution function of x and y. Okay. Of course, we're talking about abbreviating it as a joint CDF. Okay, is denoted by big F of A comma B, and given by big F of A comma B is equal to the probability that x is less than or equal to A and y is less than or equal to B. So that's its definition. And so what we can say is that f, so we want part 1, of A comma B, what it's equal to is the sum, the double sum. The first sums over all x values that maybe are less than or equal to A, that are definitely less than or equal to A, and all the y values, the sixth sum, all the y values that are less than or equal to B, of f of x comma y, where f of x comma y is the joint PMF of discrete random variables x and y. So discrete random variables x and y. And 2, f of AB is equal to the double integral from minus infinity to infinity. I'm sorry, it's not from minus infinity to infinity. It's minus infinity to B, minus infinity to A, f of x comma y, dx dy, where again, f of x comma y, we need to know what that is the joint PMF of the continuous random variables x and y. That's what we got. Okay. So for the remainder of the class, we're going to look at an example of calculating the CDF. Okay? It's going to be for discrete case. That ended today's video after we did this example. So here's the example. it's going to, we're going to let f of x comma y be equal to, well, the same joint PMF we had before. X plus y over 21 if x is equal to 1, 2, and y is equal to, I think it was 1, 2, 3. That's okay. And so someone might say, find f of AB, the CDF, the joint CDF. Now look, what's this mean? This means that this is the chance that x is less than or equal to a, and y is less than or equal to b. So we want to define this for a and b values. Okay? But here's what I'm thinking. If a happens to be less than 1, then it can't happen because the x values are 1 and 2. Okay? So here's what I can say. Note, if a is less than 1, or if b is less than 1, then when you're talking about f of ab, you're talking about the chance that x or y are either 1 or less than 1. And the chance of that happening is 0. So then, f of ab is equal to 0. I don't want to do this in a systematic way, so make sure I get everything. So we might say this is case 1. Well, I'm going to really be concentrating on A. And so here we've handled if A is less than 1. Now, case 2, if 1 is less than or equal to A is less than 2, okay, that. Then we'll consider subcases because our problem still depends on Y. And so, of course, we've already handled the case where B is less than 1. So let's say if B, so subcase 1. Let's say if B is less than or equal to, it's greater than or equal to 1 and less than or equal to 2. Then, f of AB. So, you know, what's an example of the input value we're talking about in this subcase? We're talking about something like f of 1.3, 1.7. So that's the probability that x is less than 1.3 and y is less than 1.7. Well, what is that? That's nothing more than little f, the joint PDF, of 1, 1. And I know what that is. That right there is 2 over 21. So I got that. That's this case. Okay. Now, subcase 2, we're going to be talking about B. So what if B is sandwiched in between 2 and 3, which has got a chance to be equal to 2, not 3. Remember, A is in between 1 and 2, equal to 1, possibly not 2. So here, then, f of AB, what's that? Okay, look, A is something like 1.3, and B in this case is like 2.3. So when I think about all the ways that that can happen, that means x is 1, x is 1, and b is either 1 or 2. So what we end up getting, if this is the sum, as our definition said, 1, 1, the joint PDF evaluator is, plus f of 1, 2. Let's see what these numbers are. This is going to be 2 out of 21, because we just did it. This is 1 plus 2, so that's x plus y, so that's 3 out of 21. So we end up getting 5 out of 21. What's subcase 3? Here, that's if B is bigger than or equal to 3. Then, f of AB, that's going to be equal to, so as an example, 1.3 and maybe 3.7. So we're looking for the probability that x is less than or equal to 1.3 and y is less than or equal to 3.7. That means x has to be 1, and y could be either 1, 2, or 3. talking about those probabilities. So that's f of 1, 1, the joint PDF, plus f of 1, 2, plus f of 1, 3. And so that ends up being 2 21s plus 3 21s. Remember, f of x comma y, little f of x comma y, defined to be x plus y, so 1 plus 3 is 4, all over 21, so that's 4 over 21. And so we end up getting 9 out of 21. So those are the only subcases we have for when A is sampled between 1 and 2. Okay, now, case maybe 3 is when A is greater than or equal to 2. Okay. Remember, the x values are 1 and 2. We're going to break this down into subcases. So subcase 1 again is 1 is less than or equal to B is less than 2. So here, when we talk about what's f of AB, this is like 2.3 and 1.7. So if you're saying what's the chance that x is less than 2.3 and y is less than 1.7. So what could x be that would be less than 2.3? The output values for x are 1 and 2, so it could be either 1 or 2. And then the y values that satisfy this being less than, something between 1 and 2. So if we say 1.7, it'd just be 1. So here's what we get. This is f, the probability that x is less than or equal to a and y is less than or equal to b, is the probability that we had 1, 2, plus the probability that we had 1, should be 1, 1. Okay. Plus the probability we had 2, 1. What are those? Let's see. This again is 2 out of 21, plus this is 3 out of 21, so it's 5 out of 21. Now, subcase 2. That's where B is sandwiched in between 2 and 3 in this manner. And so f of AB, like we've seen before, remember A is bigger than or equal to 2. So here we have f of 1, 1, so let's concentrate on x being 1, plus f of 1, 2, that's y can run from 1 to 2, f of, now x could also be 2, 2, 1, plus f of 2, 2, adding these together, here's what we get. 1 is, f of 1, 1 is 2 out of 21, plus 3 out of 21 for the next guy, plus 3 out of 21 for the next entry, plus 4 out of 21 for the next entry. That's 7 tenths, 12 out of 10. We have one more subcase. So for the last subcase, what does it have to do with? The last subcase is where B is greater than or equal to 3. And so f of AB, so let's think about this. So A is bigger than 2 by 2.3. B is bigger than 3 by 3.7. We want to know the probability that big X is less than 2.3 and big Y is less than or equal to 3.7. But all the output values for X, 1 or 2, are less than 2.3. And all the output values of Y, 1, 2, and 3, are less than 3.7. So this ought to be equal to 1, but the way we can write it down is f of 1, 1 plus f of 1, 1, 2 plus f of 1, 3 plus f of 2, 1 plus f of 2, 2 plus f of 2, 3. Let's see what these numbers are. So this ends up being 2 out of 21 plus 3 out of 21 plus 4 out of 21 plus 3 out of 21 plus 4 out of 21 plus 5 out of 21 when I add these together, 5, 9, 12, 16, 19, 21 out of 21, which equals to 1. And so what I'm going to do is summarize this. Okay? So I'll come over here just a moment. We'll summarize it now for your last thing. Remember, I'm doing this work primarily from that definition I gave you, exclusively from the definition I gave you from CDF, the joint CDF, where in the discrete cases it was this double sum. That's what I'm using. And so here's our summary. F of AB, here's what we want. It's equal to 0 if A is less than 1 or B is less than 1. It's equal to 2 over 21 if we have 1 is less than or equal to A, which is less than 2, and 1 is less than or equal to B, which is less than 2. It's equal to 5 over 21 if 1 is less than or equal to A is less than or equal to 2, and 2 is less than or equal to B is less than 3. It's equal to 9 over 21 if 1 is less than or equal to A, less than 2, and B is bigger than or equal to 3. It's equal to 5 over 21 if 2 is less than or equal to A, 2 is less than or equal to A, and 1 is less than or equal to B is less than 2. It's equal to 12 over 21 if 2 is less than or equal to A, and 2 is less than or equal to B, which is less than 3. And finally, it's equal to 1 if 2 is less than or equal to A, so A is bigger than or equal to 2, and B is bigger than or equal to 3. And so that's the joint CDF. Ladies and gentlemen, I thank you very much for your time and patience. That's all we're going to do.